Hello, statisticians. Mr. Youngsaber here from Skew the Script. Today we're going to follow up our in-class activity investigating whether the home teams had an advantage in the NBA bubble. Let's skew it. So today we're going to build on an in-class activity we did to introduce the formal language behind what we call hypothesis tests. This is lesson 7.4 in our course sequence. To remind you of the context behind our activity, here's what we were talking about. On March 11th at the Chase Center, which is the home of the Golden State Warriors basketball team in San Francisco, we had a full crowd watching the Warriors, cheering them on. But then by March 12th, the stadium looked like this, completely empty, devoid of fans, even though a game was scheduled for that day. What happened in between? The NBA released a press release saying the NBA season is suspended until further notice due to the COVID-19 pandemic. And so the NBA season seemed canceled. But then, out of nowhere, there was an unlikely hero that emerged. Yes, Mickey Mouse and Disney World. In summer 2020, they opened up a court at Disney World for the NBA players to play in the bubble. All the coaches, players, staff tested for COVID-19, and upon a negative test, they were able to come to the bubble and play one another in televised games on a neutral court in the bubble. So they all played on this empty court that had no team logos on it, no screaming fans, just pure basketball with a net and courts and the teams there. Here's how the bubble worked. There were 22 teams, each played 8 games to finish their season, and the home and away designations were randomly assigned for each game. There was no true home team or away team because you're not playing in your home stadium. It was just saying, okay, there are 2 teams playing this day. We're going to randomly select one to be home, one to be away, and we're going to play the game. So it was kind of arbitrary. Now, typically, home teams win 60% of their games in the NBA. And that's because when you're playing in your home stadium, you have thousands of fans screaming for you to win and trying to distract the other team. And so there's a real home team advantage, and they tend to win most often. For the NBA bubble, there wasn't a true home stadium, but the NBA did try and do a few things here and there to make it feel a little bit like home. So they had these monitors where they projected home team fans, even though they were kind of silent. They had virtual cheerleaders for the home team projected on the stadium lights, and they had some home stadium arena sounds being played. They were similar to the sounds played in their home arena. So the question is, were those little efforts by the NBA enough to make up for the lack of 20,000 screaming fans and make it seem like that there was a home team advantage? Well, here's the thing. It seems like it'd be unlikely that the home teams would actually find an advantage to all that. But here's the thing. The teams randomly assigned to be home in the bubble won 49 times. The teams randomly assigned to be away only won 39 times. So our question for today is, did home teams actually really have an advantage in the bubble? So if you'd like to follow along using guided notes, you can print them up at this URL, and we're going to investigate today. So to start with our in a world where framing. So the 88 games played, the home teams won 49 times. This is what we observed in the real world. That means they won 56% of the games played. Now let's imagine hypothesis A, which is that there's no true home team advantage in the bubble. Those home teams, they won more often by pure chance alone. They're probably winning, the probability of home being assigned to the better team was 50%. There's no true home team advantage, and so the home teams won more often by chance. Then there's hypothesis B. There was a home team advantage created by all the efforts of the NBA to make home seem like home. So the home teams won more often because they had a true advantage. It didn't happen by chance. That 56% of the time they won was because they had a true advantage. So here are 2 hypotheses about what occurred. And before we do any analysis, which hypothesis would we tend to assume? Well, in my mind, I would assume hypothesis A. It's a neutral court in the bubble. There's not even real fans in the stands. I would assume there's no home court advantage. If the home teams won more often, it's because it happened by chance alone. They randomly assigned home to the better teams more often, so it happened. If hypothesis A is true, then if we assume that one, what proportion of games will we expect the home teams to win? Well, we expect about 50%, right? Because each game, the home or away, were randomly assigned. So we'd randomly expect about half the time the home team would be assigned to the better team that day. Now, what we observed, or observation, was that home teams won 49 out of the 88 games, 56% of the time. So let's write an in a world where statement for assessing these hypotheses. So let's remind us of what in a world where feels like. So we're going to use that movie quote. In a world where there is no home court advantage, there's no home court advantage at all, what are the chances that home teams win 56% or more of the time? So in this world where the home teams have no true advantage, it's a coin flip every time, what are the chances that by chance alone, you'd see the home teams win 56% or more of the games? So let's ask that question. And let's do a simulation to try and see what the answer to that question is. So in this world, every game is like a coin flip. The probability of winning for the home team is about 0.5. So let's simulate what that looks like. And we're going to go back to the Desmos activity we used in class to do this simulation. If you'd like to do it on your own, find the screen that looks like this. So what this screen did was it played 88 games and it randomly assigned the home or away team to win with 50% probability. This is simulating the world in which the home team has no advantage, so it's a 50% chance they win each time. So let's go ahead and click and simulate a season. So here's a simulated season, and if we count it up, we see that the home team wins randomly 43 out of the 88 games played. So 43 out of 88, that's about 48%. So we could label that right here on our dot plot. So a little bit less than 50%, but pretty close. Let's simulate another season. And if we count up the number of times the home team won, it won 46%, or no, sorry, 46 out of the 88 times, which is 52% of the time. And so they won a little bit more than 50%. And so by chance alone, they got a little bit lucky. And we can do another season and another season and another season. We can keep on randomly simulating seasons. And we see that most of the time, the home team wins about 50% of the time, but there is some variation. By chance, the home teams might tend to do a little bit better or worse due to some randomness in the assignment of home or away. So imagine we did that simulation 100 times. So each of these dots represents the winning percentage of the home teams for a simulated season. So these are 100 seasons under hypothesis A, no home court advantage. What we observed in the real world was that the home teams won 56% of the time. So what we can do is take these simulations and estimate the probability of winning that amount or more by chance alone in this hypothesis A world where there's no true advantage, in this world where we simulated 50% probability each time. So it turns out that 14 out of those 100 times, the home team won by chance 56% of the time or more. So if you do 14 out of the 100 times we simulated, that's 14%. So we have a 14% chance of seeing that winning percentage or more by chance alone. So are you convinced that we can reject hypothesis A? We can say that the home team won so much in the real world that there could not have been a fair shot for home and away? Well, no. In a world with no home court advantage, there's still a 14% chance, there's still 14 out of 100 seasons where the home team won that many games by chance alone. That's too high of a chance for me to say, nope, this is too unusual, I should reject it. So what we're saying is that our observation, the 56% of the time the teams won in the real world, that isn't unusual enough in this world that we've assumed to cast doubt on hypothesis A. So now we can ask, how low would this probability have to be to convince us that there was a true home team advantage and say we can say that there was a true home team advantage? Well, we're going to keep that question pending until a further part in this video. So let's talk about how we can formalize the analysis we just did in terms of formal statistical language. And we're going to start with hypotheses. So whenever you're given a question like this on the AP exam, is there convincing statistical evidence that the home teams had an advantage in the NBA bubble? That phrase, convincing statistical evidence, usually means that you should be conducting a hypothesis test. And you're going to start by defining your hypotheses. There's always going to be a null hypothesis. This is the default belief about a parameter's value. It's often called the dull hypothesis. There's nothing new or interesting happening, and you assume it to be true until evidence convinces you otherwise. Then there's the alternative hypothesis. It's the unproven belief about a parameter's value for which you have to gather evidence to convince yourself of. It's the research hypothesis, what the study is investigating and seeking potentially to convince us of. And we don't assume it to be true. We have to collect evidence to support it. So in our case, what was the default or dull null hypothesis assumed to be true? Well, we assumed there was no home court advantage. We assumed that, they're playing on neutral court. we're going to assume the probability of winning is 50%. There is no home court advantage. And alternative, the unproven research hypothesis that we needed evidence for to see if it was true, was that there is a home court advantage. The NBA did enough with their stadium sounds and whatnot to make for a true home court advantage. Now, let's put this down mathematically. So we can define a variable P, that is the true proportion of games won by home teams if you played many games in the bubble. This is the parameter, the true probability, true proportion of the time the home teams would win if you played many games. So in the null hypothesis, we assume P is equal to 0.5. There's a 50% chance of winning. The home teams, if you play many, many games, would win exactly 50% of the time if you play this ad infinitum. And then the alternative, if there is a true home court advantage, is that it's going to be a bit higher than 50%. If you played many, many games, the home teams will win a bit more often because they have a true advantage in the bubble. So we can write down our in a world where statement with these hypotheses. So in a world where the true proportion of games the home team wins is assumed to be 0.5, what are the chances that we see what we observed? That 56% of the time in the bubble, the home teams won, or more than 56% of the time they win. So there's two possible conclusions we can get from asking this question. First, there might be enough evidence to reject the null and say, yes, we're convinced there was a true advantage, or there's not enough evidence to reject the null. We can't reject the idea that there was no advantage in the bubble. One thing to note, you can never accept the null hypothesis. You can never accept the null. You assume it to be true already in your analysis, so you cannot prove it to be true because you've assumed it. We assume there's no home court advantage. So if our observations are reasonable under that assumption, it doesn't mean we've proven our assumption, it just means that the assumption that we made at the get-go was reasonable. We assumed it, so we can't prove it because we started by assuming it. All right, so now we're going to talk about two more formalizations of this, p-values and alpha levels. So the p-value is the probability of observing your measured statistic, or one more extreme, if you assume the null is true. P stands for probability value, and it helps us determine how unlikely our sample data is under the null hypothesis. So in this case, we had our simulated seasons, and we saw that 14 out of the 100 had more home team winning by chance alone. So the probability of home teams winning 56% or more of their games in this no home court advantage of the world was 14%. That 14%, that is the p-value. That's it. That's the p-value. And the way we can interpret it is, in a world where there was no home court advantage, the null is true, assuming the null is true, there is still a 14% chance that we'd observe what we saw in the real world. The home teams won 56% or more of the time. So when the p-value is low, that means the data you observed in the real world is unlikely under the null assumption. So that means you can reject the null assumption. If the p-value isn't so low, it's kind of high, the data we observed isn't that unlikely under the null. We cannot reject the null assumption. So you might be asking, how low is that low? We can cut off between rejecting or not rejecting. That is defined as the alpha level. The alpha level is the cutoff for p-values at which we reject the null hypothesis. Commonly, we set alpha to be 0.05 or 5%. So this question we asked earlier, how low would this probability have to be to convince you there was a home team advantage, to reject the null and convince you there was a home team advantage? The answer to this question is the alpha level. And commonly, we set it at 0.05 or 5%. So in this case, we're at 14%, which is above 5%, so we can't reject the null. When the p-value is less than our alpha value, we reject the null. We have convincing evidence of the alternative. When the p-value is greater than our alpha level, we fail to reject the null. We can't reject it, and we don't have convincing evidence of the alternative. So this question, is there convincing statistical evidence that home teams had an advantage in the NBA bubble? We can answer it with this statement. In a world where there is no home court advantage in our simulated worlds, what are the chances that home teams win 56% or more of the time? This is the question in our own phrasing. That chance is 14%. That's the chance that the teams would win that percent or more often by chance alone. And so we can make a conclusion using that p-value we got. And here's a template that you can use for your conclusions. I'll use it right now. Because our p-value, 14%, is greater than the alpha level, that cutoff we set of 5%, we cannot reject the null. We fail to reject the null. We don't have convincing evidence that there was a true home court advantage. We're not convinced of the alternative. We can't reject the null. So last thing we're going to talk about today is connecting all this to confidence intervals. That's going to lead us to our discussion. So if you make a confidence interval for the situation we're talking about, the interval for the true proportion of games the home team will win based on our observed data is 0.453 to 0.661. And the discussion question for you to think about and come into class with the answer to is this confidence interval consistent with the results of our hypothesis test? I'd like you to explain your reasoning. That's it for today's statisticians. We'll see you in class.